Derivative techniques. What we're going to do in this lesson is look at some techniques that help us to find a derivative easier than writing out the entire limit definition. So I'm going to cut to the chase and get to a nice easy one. F of x equals, and I'll make up a polynomial, let's say 8x to the power of 5 plus 4x to the power of 3 minus 2x to the power of, let's say, 2. Now, many people know these techniques already. They don't need this lesson to figure out this thing called power rule, and you might already know it, but what we do is we take the exponent and we multiply it to the leading coefficient, and that becomes the new coefficient. And then we reduce the exponent by 1. So the derivative comes out to be f prime of x equals, well, let's see, we'll have 40x reduced by 1 becomes 4 plus, you could probably do it before I say it, 12x to the power of 2 minus 4x. We can do 100 of these and they don't get any harder. So here's a g of x polynomial function and we'll find the derivative. Let's see if you can't do it before me. Maybe press pause. Real nice and easy. G prime of x equals 28x to the power of 3 minus 3x squared plus, now we could be a robot methodical about this and treat this a 1, and the 1 times the 2 is 2. X to the power of 0, anything to the power of 0 is 1. Or think of this term as a linear portion, and the derivative of a linear is just the slope. So the derivative of 2x is simply 2. And then here we have a constant, and the derivative of a constant is 0. So that's the derivative. Now we have h of x. In this particular problem, I added a fractional exponent and I added a negative exponent, but the rule still applies. So we have h prime of x equals 90 x to the power of 8 plus 2x to the negative 1/2. Then we'll have minus 15 x to the negative 4. All of these problems illustrate what's called the power rule. That's where you take the power times the coefficient and then reduce the power by 1. Now let's go rapid fire just to summarize. So suppose f of x equals 3. F prime of x equals 0. It's a constant. The derivative is 0. If g prime of x equaled 5x, then g prime of x, the derivative, and notice I'm using Lagrange notation now. The derivative is simply the coefficient because it's linear, 5. H of x equals x over pi. H prime of x, again, would just be the slope, 1 over pi. We'll do another f of x equals x to the power of 5. F prime of x, 5x to the power of 4. I think you got the idea. Let me give you one more polynomial and I'll change up the notation just so we can become comfortable with both. So here, I don't know, make up something. 6x to the 5th minus 2x plus 3. And this time, instead of saying prime, we'll say find this. Now, this reads dy over dx, but we say dy dx, or the derivative of y with respect to x, the variable being x. So dy dx is equal to 30 x to the power of 4 minus 2. The power rule is nice and easy, but before the lesson is over, we will prove why the power rule works. That's what's really cool. Next, we're going to look at the product rule, which deals with a product of two quantities. Here's one quantity, and here is the other quantity. I'm going to call these terms. We have the purple term and we have the green term. The way the product rule goes like this. It's kind of like a little song. It's the first term times the derivative of the second. Now notice I didn't say second term, I just said second, implying term. Let's start over. First term times the derivative of the second, plus the second term times the derivative of the first. You should press pause and say it to yourself. First term times the derivative of the second, plus second term times the derivative of the first. Alright, so we're going to do that now to find the derivative. So f prime of x equals the first term. And then I'll show that I'm doing the derivative of the second with Lagrange notation, prime, plus second term times the derivative of the first, prime. You do not need to show this step. I'm just showing it in the notes as an option if you are sort of just trying to figure it out. But this is what you must write. F prime of x equals the first term times the derivative of the second, and I'll just do the derivative of the second, which is 20 x to the power of 3 minus 3, plus second term 5x to the power of 4 minus 3x plus 2 times the derivative of the second, which is simply 2x. And then I'm going to ask you to leave it unsimplified. So this is my answer right here, product rule. Let's take a look at the second one, and I'm sure you could do this without listening to the video. The only thing different here is I want to show you the notation difference. So we'll say we're going to find dy dx, the derivative of y with respect to x. So we have first term, and then we show that we're taking the derivative of the second term by saying the derivative of x to the power of 6 minus 6x plus 1, and then we do that with respect to x, plus second term x to the power of 6 minus 6x plus 1 times the derivative with respect to x of the first term, x to the power of 4 minus 2x. But like in the example before, you do not have to show this step here. You don't have to use that notation. What you do need to be able to do is just execute it. So dy dx equals first term times the derivative of the second, so that's going to be 6x to the power of 5 minus 6, plus second term x to the 6 minus 6x plus 1 times the derivative of the first, which is 4x cubed minus 2. There's our answer. Next, we look at the quotient rule. In the quotient rule, we have a quotient. We have a numerator, which I'll call the top, and we have a denominator, which I'll call the bottom. Here's how the derivative works. Be able to sing this song in the way that I'm singing it. Bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. Let's repeat that. Bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. So let's not get bogged down with notation. Let's just execute here. So we have bottom times the derivative of the top, and the derivative of the top, 4x minus 5, minus the top, 2x squared minus 5x plus 1, times the derivative of the bottom, 4x cubed minus 2. And then notice when I said all over, that's reminding you to do the whole thing over the bottom squared. And that's our answer. Again, I would like you to leave it unsimplified. Now we have g of x, and let's find, I want to use Leibniz notation. So let's say y equals g of x, and let's find dy dx, but this time let's show some intermediate work. Even though that's not required on an exam, let's just see how it would look. So we would have bottom times the derivative of the top, expressed as follows, minus top times the derivative of the bottom, all over, or shall I say all over the bottom squared. Okay, so we'll write the answer. dy dx equals x cubed plus 4x times 5x to the power 4 minus 2 minus x to the power 5 minus 2x times 3x squared plus 4 all over the bottom squared. Answer. I'd like to finish this section off by saying be careful in cases such as this. 5 over x. If asked to find dy dx, sometimes people will make too much work of this, and it will lead to the right answer, but for efficiency's sake, it is silly to use the quotient rule when the bottom is simply x. It works. Bottom derivative of the top is 0 minus top derivative of the bottom is 1 all over the bottom squared. So that works. But what I'd like you to do is think of this as y equals 5x to the negative 1 power, and then just use the power rule. So the answer is negative 5x to the negative 2, or simply negative 5 over x squared. Okie doke. So if I give you f of x equals 6 over x cubed and ask you to find f prime of x, would you do that? In your head, don't write anything down. Do it, multiply minus 1, and the answer, negative 18 x to the negative 4, or negative 18 over x to the power of 4. In the notes packet, it says lesson 1 continued, and it says find the first 3 derivatives of the function, use Lagrange and Leibniz notation. So let's let y equal f of x equals x to the power of 2 minus 5x plus 1. And let's do one over here. Let's call this y equals g of x, which will equal 1 over x plus x to the power of 5. And for each of these, we're going to find the first 3 derivatives using the different notations. So first, the first derivative is dy dx. Lagrange f prime of x. The solution, very easy, 2x minus 5. Now we'll find the second derivative. Now watch this notation. Well, the Lagrange is easier, f prime prime of x. This one's a little trickier. It's d squared y dx squared. I'll explain that in a moment. So let's find the derivative of the derivative, and that is clearly 2. Then the third derivative is d cubed y dx cubed, which is f prime 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 of x, which equals 0. You could probably see that every derivative after that, the fourth, the fifth, the sixth, will all be 0. Take a moment and find the first three derivatives of the yellow function g of x, then press pause and check the solution. And here are the solutions. You might notice that no matter how many times we take the derivative of g, it will never exhaust to 0. Now, why this notation? Well, if I'm trying to find the second derivative, what I'm really finding is the derivative of dy dx with respect to x. See that? So then it becomes d squared y, and then technically dx squared. That explains Leibniz notation. The last thing before the proofs are what I like to call theoretical derivatives. Let's see. Let's find the derivative with respect to x of x to the power of n. So x to the power of 5, x to the power of 10. How does that work? You should see that this is n x to the n minus 1. Alright, let's find the derivative with respect to x of f of x times g of x. First term times the derivative of the second plus second term times the derivative of the first. So we have first term times the derivative of the second plus second term times the derivative of the first. Yay. How about this one? Derivative with respect to x of f of x over g of x. Bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. Now, what's interesting about this, if you flip to the front page of the packet, there was a bunch of what looked like hieroglyphics, but now if you've done this and worked this out, you have discovered the way to write the properties. We have the power rule, the product rule, and the quotient rule. Let me add a couple examples to this set. Suppose I had, let's use prime notation now. Suppose I had 2 f of x minus 5 g of x, and I want to find its derivative, indicated with a prime. It's pretty easy, but I want to show you that if I asked you to find the derivative of 10 x to the power of 5, what you could actually do is take the 10 out, the coefficient, and do the derivative of x to the power of 5. So that would be 10 times 5x to the power of 4, which leads to 50 x to the power of 4, the thing you already know. So coming over here now, this would read 2 times f prime of x minus 5 times g prime of x. And just one more. Let's suppose I had f of x over 2g of x. 2g of x, prime that is, 2g of x times f prime of x minus f of x times 2g prime of x all over 4g of x squared. Like that. theoretical examples. You are now ready to prove some of this stuff.